Hey everyone, I'm back with another Pi Day video. This year I found pi experimentally using Euler's critical buckling equation. Let's say you have a rod with diameter d and length L. If you start applying a force directly down its longest axis, eventually it will bend or buckle. Can we know how much force it will take to make it buckle? In the 1700s, a really smart guy named Leonard Euler asked just that, and derived the critical buckling equation to answer it. He found that the force P to make the rod buckle is equal to pi squared times E times I, all over the length of the rod squared. What are E and I, you might ask? Well, E is the modulus of elasticity of whatever material the rod is made of, basically how resistant a material is to being deformed, and I is the second moment of area of the rod, a quantity that cares about the cross-sectional shape of the rod. For 304 stainless steel, the material I'll be using in my experiment, the modulus of elasticity is around 200 gigapascals. And for a circular rod, I is equal to pi r to the fourth over 4. The radius of the rod I'll be using is 0.00075 meters. Let's rearrange the critical buckling equation to find pi. After moving everything around, we get that pi is equal to the cube root of 4L squared times the critical buckling force over r to the fourth times E. All we need now to calculate pi experimentally is the force it takes to make the rod buckle. I'll be doing this by placing a rod with a known length between the jaws of a set of calipers and closing the jaws while using a scale as a backstop. The critical buckling load will be the highest number the scale reads out. This number will have to be multiplied by acceleration due to gravity, 9.81 meters per second squared, to get a force in newtons. As you can see from the video, the highest readout from the scale was 5.6 kilograms. After plugging that into our equation, we get that pi for 2025 is 3.33. I think that's a pretty good result. Thanks for joining me in another Pi Day celebration. Cheers.